Hello and welcome back to the part 2 of UV visible spectroscopy. In part 1 video, we have discussed about the basic introduction about UV visible spectroscopy, the electromagnetic spectrum, Beer-Lambert law and chromophores and auxochromes. In this video, we are going to discuss about the factors affecting UV absorption. So let's get started. There are various factors which affect the position of UV visible band in UV spectra. For example, the conjugation, steric hindrance, solvent, pH, etc. Let us discuss these factors one by one. The first factor is effect of conjugation. Now let us suppose we have carbon-carbon double bond. It is composed of sigma and pi bond. Now this pi bond is further divided into pi and pi star. Pi is the bonding orbital, pi star is the anti-bonding orbital. This is pi and this is pi star. Now, in pi orbital, we have these two electrons. When these electrons are excited, then they goes to the pi star orbital and this much amount of energy is required for the excitation. This is the orbital structure of pi bonding orbital and this is the orbital structure of pi star antibonding orbital. Now let us suppose we have conjugated double bond. Then we have one sigma sigma bond and one pi pi bond in the double bond. When these two pi orbitals combine with each other, then they are divided into four different orbitals called psi1, psi2, psi3 and psi4. These are psi1, psi2, psi3 and psi4. This psi4 and psi3 upper two orbitals are the anti-bonding orbitals. Psi1 and psi2 are the bonding orbitals. Now, if we fill the electrons then in the bonding orbitals, this is the highest occupied molecular orbital. And in the antibonding, this is the lowest unoccupied molecular orbital. So basically, when the molecule gets energy, the excitation of electrons takes place from HOMO to LUMO, whether it is the conjugated system or it is the non-conjugated system. So ultimately, we have to see that the electrons are getting excited from HOMO to LUMO. When there was the isolated double bond, then the the electrons have to uh, travel from when there was a isolated double bond, then this was the HOMO and this was the LUMO, and this much amount of energy was required for the excitation. On the other hand, when the system was conjugated, like when we had two conjugated double bonds, then what happened? When the molecular orbitals divided into four different parts, then these are the no new HOMO and LUMOs. Now we can see the energy difference between HOMO and LUMO. When the system is conjugated, then the energy required for excitation is this much. Now we can clearly see that when the system was having only one double bond, then this much amount of energy was required from HOMO to LUMO, but when the system was conjugated, then this much amount of energy was required for transition from HOMO to LUMO. So we can clearly see the difference between the amount of energy required for the excitation. Now, energy is inversely proportional to the wavelength. If less energy is required, then it means the lambda value will increase. So ultimately, what we can conclude that when the conjugation is introduced in any molecule, then less energy is required for excitation, or we can say that the lambda max increases. The value of lambda increases, or the absorption maxima increases in the spectra. So this is the easy representation of the excitation of HOMO and LUMO in non-conjugated and conjugated system. So we can clearly see the difference in the energy required for the excitation. Again, this is pi and pi star. When this is the isolated double bond, this is also isolated double bond, and this much amount of energy was required. But when the system became conjugated, then they uh, they got divided into psi 1, psi 2, psi 3, psi 4, and now these are the new HOMO and LUMOS. This was, sorry, HOMO and LUMO. Now only this much amount of energy is required. So when conjugation is introduced, the lambda value increases because energy required is less, and energy is inversely proportional to the lambda value. Similarly, in case of conjugated carbonyl compounds, for example, we have this carbonyl, this. This is the alpha beta unsaturated carbonyl compound. We are comparing it with C double bond C isolated double bond and the carbonyl. When there was the isolated double bond, then it can have the transitions from pi to pi star. On the other hand, in case of carbonyl system, there are lone pairs of electrons on oxygen. So it means carbonyl has non-bonding electrons, it has pi bond. So there are two types of excitations possible: pi to pi star and non-bonding to pi star. So there are two transitions possible in carbonyl. So it can have n to pi star and pi to pi star excitations, and this can have pi to pi star transitions. Okay. Now we can see that 175 nanometer was the lambda max when pi to pi star excitation was taking place in isolated double bond, and in case of carbonyl system, pi to pi star 190 was the lambda max for the excitation from pi to pi star, and this is the non-bonding electron. 280 nanometer was the wavelength when the excitation was taking place from n to pi star. When all these orbitals get combined, they generates new molecular orbitals. For pi to pi star, this much amount of energy is required for excitation, and for n to pi star, this much energy is required for excitation as compared to this pi to pi star. So we can see that when the system becomes conjugated, then what happens? For n to pi star, less amount of energy is required. Less amount of energy is required means lambda is more. So we can see that in the isolated system, the n to pi star was 280 nanometer, whereas in the conjugated system, the lambda got increased and it became 320 nanometer. Similarly, in case of pi to pi star transitions that we have already seen in the alkenes also, conjugated alkene, for pi to pi star system, the 190 nanometer was the lambda max, or in the alkene it was the 175 nanometer, and this much amount of energy was required for the excitation. But when the system became conjugated, then the lambda max was 230. Lambda max increased because now the less energy was required for the pi pi star transitions. We can compare these excitations with pi to pi star. From these two examples of conjugated carbonyls and the conjugated alkene system, we can conclude that more is the conjugation, more will be the lambda max. So ultimately, a situation becomes in some of the molecules that lambda max falls into the visible region. Visible region is from 400 to 800 nanometer. Okay, so this is beta carotene. It is red in color because it has lot of conjugation in this structure. So the lambda max becomes 452, which falls in the visible region. That's why the beta carotene is colored compound. Similarly, cyanidine chloride. It is also a plant pigment which is colored. Its lambda max is 545 nanometer because this compound also has lot of conjugations. Similar is the reason for malachite green, that its lambda max is 617 nanometer because of the lot of conjugated system. Now the second factor is effect of steric hindrance. Now the second factor is effect of steric hindrance. Means steric hindrance can also affect the lambda max value, that we can see from here. This is the molecule where this is the cycle. Now the second factor is effect of steric hindrance. Let us see first example. This molecule appears like to be planar, but actually this molecule is not planar. In this molecule, it has two double bonds at adjacent carbon atoms. Now, if this molecule has to be conjugated, properly conjugated, then all the orbitals should overlap with each other properly. But what happens that this molecule no longer remains planar because of the positioning of these double bonds at the adjacent carbon atoms. These the positioning of these double bonds create steric crowding. That's why this molecule is not planar, and these two double bonds are no longer that much in conjugated system as they should be in the ideal conjugated system. So we expect on the basis of the conjugated system that the lambda max should be 237 nanometer, but actually we get 220 nanometer as the lambda max of this value. That is because of the steric crowding of these two double bonds, which makes the conjugation less effective, and that's why the lambda max value decreases. Now let us see the second example of stilbene. This is cis stilbene and this is trans stilbene. We can clearly see the difference in the lambda max value of both the molecules. Here, the bulky groups are very close to each other. Because of the steric crowding, the whole system is not that much conjugated as we expect them to be. On the other hand, in the trans system, the bulky groups are far apart from each other. So there is no steric crowding between the bulky groups. So this is properly conjugated and planar system. That's why all the orbitals are overlapping with each other very properly. That's why the lambda max value of trans stilbene is more as compared to the cis stilbene. Here is another example of biphenyl. This is the biphenyl which is unsubstituted. Its lambda max value is 250 nanometer. But when it gets substituted with methyl group at this position, then what happens? The biphenyl system no longer remains that much planar. The copolarity is lost because of the presence of this methyl group because it creates steric crowding. Now there is poor overlap between the orbitals which leads to the shorter wavelength. So now the value of lambda max is decreased. Similarly, in another example, we can see that this is the biphenyl system. Its lambda max value is 266 nanometer. This is another system which is not biphenyl system but has one of the part of the biphenyl system, and its value is also 266 nanometer. How come? Because in this biphenyl system, the two benzene rings are no longer the planar in nature, they are rather at right angle to each other. If one ring is in the plane, another ring is in the vertical position. So, all of the conjugation is lost because of the steric crowding between these four methyl groups. Now, this molecule behaves like that this is the individual, this type of molecule. That's why the lambda max for both the systems are same in both the cases. The third factor is effect of solvent. Here, this is the pi to pi star system. Now, when we change the polarity of the solvent, we are increasing the polarity of the solvent. Then what happens? The polar solvent like dissolves like dissolves like. On this principle, the polar system will stabilize the polar state more as compared to the less polar state. Now, this pi and pi star, if we compare these two states, the pi star is more polar as compared to the pi system. How come? This is the C double bond C. In pi system, the electrons are like this, but in case of pi star, the electrons are like this. Now, in the pi star system, there is charge distribution between the atoms, which makes it more polar as compared to the pi system. So, when we change the polarity of the solvent, then this polar solvent stabilizes pi star state more as compared to pi. So, we can see this is the transition from this position to this position. Now, it has stabilized more as compared to the pi star system. Here the stabilization was this much, and for pi star this was this much. So ultimately what happens now, if we compare these two energies for pi star transitions, we can see that now less energy is required. If less energy is required, means lambda becomes more. If less energy is required, then it means lambda value will increase. So it means for pi star transitions, if we change the polarity of the solvent, or we say that if we use the polar solvent, then there is the increase in the lambda max value. On the other hand, let us see the case of n pi star transition. Here, if we compare the polarity of non-bonding and pi star state, non-bonding is already the polar system, and the pi star is also a slightly polar system as compared to the non-bonding state. So, if we compare the polarity, non-bonding is more polar as compared to pi star. Here again, like dissolves like. On this principle, the polar solvent will stabilize the more polar state more as compared to the another state. Here the polar solvent will stabilize the non-bonding state more as compared to the pi star. So ultimately what happens here, the N to pi star transitions, this much amount of energy was required, but when the solvent was changed to be more polar, then this amount of energy was required for transition. Now we can see that here energy required is more in polar solvent, so lambda is less. So lambda max becomes less in the polar solvent. So for N to pi star transitions, the lambda max value is decreased with the increase in the polarity of the solvents. The last factor is effect of pH. Let us see first example. This is phenol and it has two lambda max values, 210 and 270 nanometer. One is due to pi star transition, another is due to N to pi star transitions. Now, which one is pi star and which one is N to pi star? That we can see from the this epsilon value. The E value is 1500. It means this is the forbidden transition. So the intensity is less for this 270 nanometer peak. Now which one is forbidden transition? N2 pi star is the forbidden transition. So 270 is due to N2 pi star transition and 210 is due to pi to pi star transition. Okay. Now in phenol, this lone pair of electron is taking part in the conjugation. So the value is 210 and 270 nanometer. When the base is added, then what happens? This H is eliminated from this molecule. Now this oxygen has complete negative charge. Now it has 3 lone pair of electrons over it. Now this electrons can contribute more for the conjugation with the benzene ring, because now all the electrons are freely available for the conjugation. So that's why the lambda max value increases. Here 210 becomes 235 and 270 becomes 287 nanometer. The conjugation increases due to resonance, hence shift to the longer wavelength. So lambda max value is increasing if we add the base into the phenol. Another example is the aniline. Here this is 235, 285. Now on the basis of this intensity value, this is N2 pi star transition and this is pi to pi star transition. Now in this aniline, the lone pair of electrons are taking part in the resonance. When we add acid to the aniline, then what happens? This lone pair electrons takes up one proton and it becomes positively charged. Now, the connection of the resonance of this functional group is lost with the benzene ring. Now, there is no resonance because now nitrogen becomes electron deficient. Now, there is no lone pair of electrons are present for the resonance. So, this is like benzene only. So conjugation decreases, the resonance decreases. That's why the value of lambda max also decreases. Now 235 becomes 203, 285 becomes 254 nanometer. Thus the presence of acid or the base affects the position of lambda max values. This is another example of phenolphthalein. In the basic conditions, it is deep pink in color, but in acidic conditions, it is colorless molecule. How does it happen? That phenolphthalein, when the base is added, the proton is lost from here and negative charge is generated over this oxygen atom, which increases the conjugation in the whole system. This ring also opens up, the lepton ring opens up, and we can see the movement of all the electrons with these red arrows, that these electrons are distributed all over the molecule. Now conjugation is increased with the addition of base to the phenolphthalein. As the conjugation is increased, the lambda max falls into the visible region, and that's why it shows a pink color in the basic conditions. Here, the lambda max is 553 nanometer, which falls in the visible region. Earlier, it was 275 nanometer in case of acidic conditions. That's why the phenolphthalein give pink color in basic conditions and it remains colorless in the acidic conditions. So these are the all factors which we have discussed: the conjugation, steric hindrance, solvent and pH. If you have any doubt, you can leave the comment in comment section. I will definitely reply for your queries. In my next video, in the third part, we will discuss about the Woodward-Fieser rule for alkenes, the conjugated dienes.